So let's start off just by defining the particle model. It's really just the idea that we would take a more complicated object, like me, and just represent it as a single dot. So we can just mark my location as a single dot. And the point of that is just then it would be easier to mark my location as time changes. This could be time 0, time 1, time 2, time 3. And this that I just drew then could also be called a motion diagram. We are using particles, dots, to map out my motion as time changes. If my motion diagram was to look like this, and we could say, well, let's start my stopwatch here, and we'll call that time of 0 seconds. I'll write 0s. And then here, this might be at a time of 1 second. And then this one would be 2 seconds. During this 1 second, I traveled further, meaning I was going faster. Covered more distance in 1 second. And during this time interval from 1 second to 2 seconds, I didn't cover as much distance because I was going slower. So for the first part of this class, we're only going to study motion that's backwards and forwards along a line, and so that would be called one-dimensional. Which can be abbreviated as 1D. So I'm going to imagine a bug that starts off here at time of 0 seconds. I'll start my stopwatch then. And then the bug will end up over here at 1 second. And then maybe at time of 2 seconds it can be over here. So the bug would have first walked to the right, stopped, turned around, and then walked to the left. So if we wanted to make a table of its position versus time, or even make a graph of it eventually, we're going to have to lay down a ruler, a coordinate system to keep track of its position. And so I've sketched out a little ruler here. And I'm going to set my 0 of my ruler at where the bug's first position was at 0 seconds. And that was my choice. Somebody else could have put their ruler this way. Put 0 there. You choose where to put it. Somebody could even have put down their ruler this way. So that maybe positive numbers, positive 1, positive 2, positive 3, would be off to the left. That's your choice. So this ruler that I lay down is called a coordinate system. And usually we draw an arrow on one end of it, and that's going to illustrate which way we're counting positive. So these numbers are the positive ones. And if you were to go past 0 this way, past your origin this way, you'd end up negative. And I'm going to call it the x coordinate. So this would be like x equals 0, x equals 1, x equals 2, x equals 3. So how about I go ahead and make a table? Time in seconds, and the position along the x ruler, along the x coordinate, and how about we say that that's in centimeters? We'll assume 1 centimeter, 2 centimeter, 3 centimeters. So at a time of 0, my bug was at a position of 0 according to my ruler. At a time of 1, the bug looks like it was about at a position of 3. So time of 1 second, position of 3. At a time of 2 seconds, it had a position of -1, and the negative is basically indicating a direction. It's saying left of the origin. 2 seconds, -1. So I told you how I chose to put my ruler down here and set my origin at that position. But that can also go for time. I'm like, traditionally when you start a stopwatch, it starts at t equals 0 and counts upwards. But there's no reason why you can say, I want to start my stopwatch at 10 seconds or 30 seconds. That's your choice. Usually this is the default. It's the easiest one to use. Now, let's talk about the time interval. So you can call it the time interval, or you could call it the change in time. But another way to abbreviate that, because we end up using this idea a lot, is for the idea of change in. We're going to abbreviate that with a little triangle, and that's the Greek letter delta. So delta t represents the change in time. Another way to think of it, besides just change in, it's also going to be final minus initial. So it'll be the final time minus the initial time. Final minus initial. So if we say, what is the time interval? And let's do it for the whole diagram here, from the very, very beginning to the very, very end. We'll say the change in time, delta t, is equal to the final t, so we'll say t with a little f, minus the time initial. And these little subscripts here, the t and the I, are just notes to ourselves. So then the final time was 2 seconds minus the initial time of 0 seconds. So then our time interval, our delta t, was 2 seconds. Now, displacement is going to just be a fancy way of saying change in position. And since we have a change in, we can abbreviate that with a little triangle, a delta, and our symbol for position was the letter x. So our displacement, our change in position, is going to be the final position minus the initial position. So if we go back to the bug example, our final position was -1, and our initial position was 0. So final position, -1 centimeter, minus the initial position, 0 centimeters. So we'll end up with -1 centimeters. And in this case, that makes sense to me. Right? And we can see that on this figure, going from the initial to the final. If I drew that as an arrow, it would be pointing left. And so that -1 really just means left 1. Now notice that that's not the same thing as distance traveled. The bug went further. The bug went 1, 2, 3, 4, 5, 6, 7. The distance traveled was 7 centimeters. But the displacement doesn't care about that. It only cares about the change just between those two, final minus initial. Distance traveled for bug. The abbreviation for distance traveled is usually just a little d, so we could say the distance traveled was 7 centimeters. And the distance traveled can't be negative, kind of like the odometer in your car can't be negative. Right? It's just going to keep counting how much further you go. Whereas the displacement can be negative.